How entanglement actually works. Quantum entanglement begins with a situation that feels ordinary at first. Two particles are created together in the same physical interaction under conditions that tightly link their properties from the very start. This usually happens because certain quantities must be conserved. If one particle has a particular property, the other must balance it. From the beginning, the system is constrained to behave as a whole. At that moment, the particles are not two independent objects in the way we normally think about things. They form a single system, even though they can later move apart. What makes entanglement strange is not that the particles communicate, but that their properties are not fully separate. Certain qualities, such as spin or polarization, are only defined in relation to each other. Before any measurement occurs, neither particle has a definite value on its own. Instead, the system exists as a set of possible outcomes at once. This is not uncertainty caused by missing information. It is uncertainty built into the structure of reality itself. When a measurement is made, something important happens. Measurement does not mean observation by a person. It means interaction. The particle interacts with a measuring device, the environment, or another system strongly enough that one outcome becomes fixed. At that moment, the shared system is forced into a specific state. As a result, the corresponding property of the other particle becomes defined as well, regardless of the distance between them. Not because information traveled, but because the information was never stored separately. This is the point that often causes confusion. Nothing is sent. No signal moves faster than light. No message is exchanged. The result appears instant because the system was always described by a single relationship. Distance does not break that relationship. What changes is not the distant particle itself. What changes is how the system must now be described after interaction has occurred. Before measurement, multiple outcomes are allowed. After measurement, only one remains. This is why entanglement cannot be used to send messages. You cannot control the outcome of a quantum measurement. You only discover it. The result you observe is random, even though it will always be correlated with the result observed elsewhere. Those correlations only become visible when results are later compared using ordinary communication. Nothing meaningful is known until that comparison happens. This preserves causality. No usable information ever travels faster than light. Entanglement is often demonstrated using pairs of photons. Their polarization states are linked. If one photon is measured in a certain way, the other will always show a corresponding result when measured along the same basis, even if it is far away. This correlation was not created by the measurement. It existed from the moment the pair was formed. Experiments have repeatedly confirmed this behavior. They rule out explanations based on hidden signals or prearranged instructions carried by the particles. The correlations observed are stronger than anything classical systems can produce. This is what makes entanglement fundamentally non-classical. Entanglement does not mean particles lose all individuality. They can still interact with other systems. But once those interactions become strong enough, the entanglement begins to weaken. This process is called decoherence. Decoherence explains why entanglement is fragile in everyday environments. Interactions with air, light, heat, or other particles quickly disrupt the shared quantum state. This is why entanglement is difficult to maintain outside carefully controlled conditions. At the microscopic scale, entanglement is common. At the human scale, it is almost impossible to preserve. Modern physics no longer treats entanglement as a curiosity. It is considered a resource. Quantum computers use entanglement to explore many possibilities at once. Quantum encryption uses it to reveal eavesdropping. Quantum networks rely on it to link distant systems in coordinated ways. In none of these cases does entanglement transmit information faster. Instead, it changes how information is structured. The deeper lesson of entanglement is not about speed. It is about separateness. At the quantum level, the universe does not always divide cleanly into independent parts. Some systems must be described as wholes, even when their components are far apart. So when we say two particles are entangled, we are not saying they are communicating across space. We are saying that, in a very real sense, they were never fully separate to begin with. And that is how entanglement actually works. Thanks for watching. Did you already know this is how entanglement works? Or did something surprise you? If there's something else you'd like explained, let me know in the comments. And if you liked the video and the way I explained things, please like and subscribe. This will really help me and the channel to grow. Till next time.